Okay. Okay. Since you switch off the light, the brightness has gone from this. No, I should increase it. Where is the brightness? Above? Sound.
Yeah. The display and brightness.
No, which one? So, which one? The screen?
Below general.
Below general. Okay.
There. Display and brightness.
Okay. It's too low, slightly. Good. Okay. Okay, so we are going to discuss a new topic, which is about unbounded operators. Okay, and you can't avoid these things. So I have told you where we encounter that, and it's precisely there we will encounter. It comes as the generator of some operator unitary group or something. Okay, generator whatever. If you have some unitary group which satisfies this condition, ut times us equal to us plus t, and st are in R. And you have a unitary group like this, T, a collection of unitaries indexed by R. Then this UT is given by e power IAT for some A, which is a self-adjoint operator in the sense of unbounded operator. Okay. And conversely, given any such self-adjoint operator, I mean, by self-adjointness, it actually, it means that it has to be whatever I mean by densely defined and all that. And I'm going to erase this. And because we will see all these things again. So for this reason, we need the theory of unbounded operators. So what is an unbounded operator? It is just any linear operator. But then for an unbounded operator, we need the following, following informations. It's not some defined on some vector space or some non-linear space, something like that. It has to be in a Hilbert space. Okay. So we have to deal with some Hilbert space, the Hilbert spaces. But the point is the unbounded operator will not be defined on the whole of Hilbert space. It cannot be defined. Okay. I will tell you why it cannot be defined sometime. I mean, most of the time. Okay. Some of the unbounded operators may be defined. But mostly, for example, when it is adjointable, that is the operator we will be dealing with. When it has an adjoint, then it will make sure it's bounded. If you have an operator, some linear operator, defined on the whole of Hilbert space, that means it's defined on a closed subspace. I mean, even now it's a closed subspace. The subspace would not, the domain of the linear operator, if it is closed and it has an adjoint in some sense, then it will automatically be bounded by what is called closed graph theorem. You haven't seen, have you seen closed graph theorem? It will be taught in Ghana too. Okay. But if you have already, if you know that, then we will discuss graph anyway. So I will mention what is closed graph theorem. I will not prove it. Actually, the proof of closed graph theorem involves what is called open mapping theorem. And the proof of open mapping theorem involves what is called bare category theorem, which you might have seen in second year BSc analysis course. Analysis 3 bare category theorem is there. So you have to see bare category theorem. And from that it follows. Okay. So HK are two Hilbert space. Now D contained in H. Okay. A linear operator, just D to K, is a linear operator. Of course, you know what is linear operator. Okay, we will deal with this, and D is the domain. And we will denote by range of D. Sometime I write ordinary D. I mean, I hope I will always write strict D. Otherwise, ordinary capital D is also domain only. Range of T is just the range of T. R of T is just the range of T. So, which is contained in K. The range is important because it's contained in K. Suppose, I mean, T is suppose an injective operator, then you can define the inverse on the range of T. Right? You can just define on the map. This is just the definition. You don't need anything else. For bounded operators to be bounded, it has to satisfy that condition. There is nothing. It is just a linear operator defined on a domain containing H. The information about H is important. And we say T. we say T is densely defined if D also we can call it as D of T. Okay, sometime D of T I will write. Okay, because when there are two operators, we have to write it D of T or T of T. Okay, you can call it D of T or just D when there is only one operator. Okay, D of T is the domain. D of T is dense. That's all. So if it is densely defined, then it is densely defined. That's what it means. Okay.
So the R of T is gamma.
R of T is
Like what's it?
R of T is just contained in K. Contained in K. This is contained. I just said contained in K. For instance, if T is the nice thing about, see, if you want to talk about, when you talk about bounded operators, which is defined on the whole of Hilbert space or anywhere, then if you want to define the inverse, you have to think about the onto condition, right? You have to, it should be 1, 1, it should be onto, and the inverse has to be bounded. You have to think about all these conditions. But here there is nothing. We can, for example, this is so nice in this sense. If T is injective, free from D of T is injective, then we can define T inverse from R of T, right? R of T to H. Okay. In fact, it will land up in D. So you don't need any condition. If it is injective, then there is an inverse. Injective, just 1, 1 is enough. You can take the range because it's not fully defined. It's not defined on the whole Hilbert space. Okay. So, but it is important since we are talking about densely defined and all that, the information about H, where it is contained in, that's very important. It may not be dense in a bigger space, and then we cannot do, because we are going to deal with adjoints and other things. So it will not work. So the information about H and K is also important.
Here D of T is any subset of H.
Any subspace. Subspace. Yeah. D of C is subspace. Domain is subspace. Any subspace, if it is dense, we call it densely defined. That's all. That we have made only this definition. Okay. You have a subspace where it is defined. It can be whole of H also. Then it will be bounded or it may not be bounded. That's different. Okay. So fact. T, if domain of T equal to H, we don't even need that. We will be seeing that if domain of D is H, or if it is closed or something, if it is closed, or if it is closed is enough. Or complete. I mean, if you don't have anything else, if it is contained in something, it has to become closed. If it is contained in some H, you have to say it's closed. If there is no reference Hilbert space, then you have to say it's complete or something. Okay. DFT is closed, and there exists a T star from K to H. Okay. Or it's not even K, it has to be some from K to H. Okay. Such that Txy equal to X T star Y. Okay. Then T is bounded. That is, T is adjointable. Adjointable means there exists an adjoint. Adjointable implies T is bounded. On the other hand, T is bounded means it's adjointable. That we have seen. That follows from Rees lemma and other thing. So adjointability and boundedness for functions for operators defined on a closed subspace are equivalent. Okay. So this way I'm not proving. This follows from closed graph theorem. Anyway, I will state what is closed graph theorem, which also I'm not proving. Closed graph theorem. So you can define graph of T. So let T be T from H to K. It defined on H, okay, where H is a Hilbert space. T is defined on whole of H, okay, H to K. And you define the graph of T equal to all those X, Tx, okay, where X is in H. This is contained in H cross K. I mean, H direct sum K if you want. H cross K and H direct sum K are same, right? H direct product is the direct sum. The tensor product is we take the direct product, do something else, take the span and do something. Okay. The direct product, you direct product and depend on what kind of norm you are going to put. Okay. That depends on so direct sum. You can put this is exterior direct sum. You can take interior direct sum also. This is exterior direct sum. If you the inner product is take the inner product, I mean the component wise, and then sum it. Okay, that's the G of T is closed. It's a closed subspace. Okay. So this is true. This is only true for so if I mean it's a closed subspace, then T is bounded. Or let's not even do that. Let's just I mean it's clear the other way. So you have a T, you have a G of T, then T is bounded if and only if G of T is closed. G of T, so let me just tell you what it means by G of T is closed. G of T is closed. That means this is equivalent to saying Xn, Txn converges to some Xy. Okay. Then Xy should also be in G of T, right? That is what it means by graph of T is closed. Okay. If there is a limit of with the sequence converging, that is, this is equivalent to saying Xn converges to X. The nice thing about something is, if you want to say what is the use of closed graph theorem? If you want to say some function is continuous, then you have to say Xn converges to X, f of Xn should converge to f of X. Right? Here it's not like that. Here it's much more simple. Xn converges to X and T of Xn converges to Y, then T of X should be equal to Y. That's what it says. Which is a very weak criterion, right? Graph of T being closed is very weak criterion. Certainly, if it is bounded, this will hold. Closed graph theorem says the other way is also true. So this is the condition for graph being closed. Graph is closed means Xn converges to X and T of Xn converges to Y, then Y should be equal to T of X. Okay, this is what the graph is closed. And I have just written the definition, right? G of T is closed. The graph is closed means there exists sequence in the graph which converges to something in the space in the H direct sum K, okay, which is some element XY. That means Xn converges to X, Txn converges to Y, and then you should have that it is in the graph means Y should be a T of X of something. It is in the graph means Y should be T of X. That is what it means. It is in the graph. Okay, so Y should be equal to T of X. That's all. Here we will. I mean, this is for Hilbert space. It is defined. If it is for an unbounded operator, I will come to that anyway again. So this is about closed graph theorem. So this is closed graph theorem says that if the graph is closed, it is bounded. It is clear that if Xn converges to X, if T is continuous, Xn converges to X, T of Xn will converge to T of X. Certainly the graph is closed. On the other way, closed graph theorem gives a very nice criterion for boundedness, provided the operator T is defined on a Hilbert space or a Banach space. If Banach space is enough. Okay? This is a theorem on Banach space. That's all. Okay, so this is about closed graph theorem. Now we want to talk about unbounded operators. This is not true for a general. I mean, if it is not defined on a Hilbert space, it's not true. The example is differential operator. Let us counter example. You take your, I mean, here I'm dealing with Banach space. Okay, please don't mind. So this is just C of 0, 1. Let us take. This is my X. Okay. A Hilbert space also you can write it. I mean, there are examples. We'll see closed. I mean, we'll see plenty of closed. I mean, all our examples we are going to deal Selford giant. They have closed graph. Okay. So the closed. They are also called the operator which have closed graph are called as closed operators. Okay. So we will see plenty of closed operators. Here I am giving a very easy example. X is C of 0, 1. And we define C1. Okay, C1, you already know what is C1. This is just all differentiable. I mean, functions which are differentiable and the derivative is also continuous. So this is dense there. Now you define D, capital D. D from C101 to C01, which take just derivative, F going to F prime. Okay. You know that this is not continuous. We have already seen in the Ghana class. Okay, this is not continuous. Okay. But then the graph of D is closed. Graph of D is closed means what? F1 converges to F and F1 prime converges to some G. Then F prime equal to G. This is true. F1 converges to F uniformly. Okay. In the norm infinity. The uniform norm, not point-wise convergence. Point-wise convergence, this is not true. If F1 converges to F uniformly, the derivative F1 prime converges to some G uniformly, then G should be equal to F. So the graph of a differential operator is closed, but it's not bounded. So this is the counterexample for closed depth theorem. Okay, counterexample means the operator has to be defined on the whole of input space. Okay. So as I said, from closed depth theorem, that statement, if something is adjointable, then it is actually bounded. So anyway, we are not going to deal with bounded operators. We are going to deal with purely unbounded operators when we look at strongly continuous semigroup. Okay. So let us go to the examples. Let us talk about adjoint of a. So this is definition. Before definition, let us make a proposition. So suppose T from D is contained in H, of course, to K, be densely defined. We will not deal with other operators, okay? Densely defined operators. Okay. Then the following are equivalent. Two conditions are true. One, following are equivalent for a Y in K. Okay, for a Y in K. The map there exists a C, K or C or whatever, K greater than 0, the real number greater than 0, such that inner product Txy, Y is in K, Tx is in K, is less than or equal to K times norm X. Okay. This just means X going to Txy is bounded on domain of T. Okay, domain of T. Okay. Second condition, the equivalent condition is there exists a Z in H such that Tx y equal to X. Proof is clear. How many of you the proof is clear? Immediate. It is just Rees-Lemma. First one says, you have an operator. What do you have? You have an operator T defined on domain of T to K, and D of T is dense. It is densely defined. Now you have this Txy, the inner product is equal to K norm X. That just means this for all X. Okay, this is for all X. DFT. For all X and DFT. Okay. That means the map, the map X going to Txy, which is a linear functional. From D of T to complex numbers. That is this map. Proof 1 implies 2. The map x going to txy, which is from d of t to c, is bounded. So it extends to h. Any bounded linear functional defined on dimensional space will extend. So because it extends, there exists a z such that then reach Ramma implies there exists z in h, okay, such that that map is actually given by xz. Right? That's all. Okay. So 1 implies 2 is clear. It is just reach Ramma. So I mean, it's also x going to txy is bounded. Okay. So there exists a z such that this happens. On the other hand, suppose there exists something like this. You want a k, you just take this is just Cauchy-Schwarz. That k is, I mean, txy is norm z times norm is, which is that k is just norm z. That way is clear, right? 2 implies 1 is just Cauchy-Schwarz. You want a k such that norm tx times norm y, I mean, tx norm y is equal to x z, it is saying. That's what the second condition is saying. Certainly that is less than or equal to norm x times norm z. You take k equal to norm z. That's all. Right? 2 implies 1 is clear.
It's continuous.
Which is continuous?
Inner product x from z.
Yeah, but inner product is not a linear. I mean, if you fix one of them, yeah, it is basically Cauchy-Schwarz.
Yeah.
It's from, I mean, that continuity follows from Cauchy-Schwarz. Okay, that's all. So what does it say? It says that if this map x going to txy is bounded, or if there exists a constant like that, this is a condition 1 is the important condition. Whatever the condition every time. Txy is less than or equal to k times z. For y, this is the condition on y in the range, not in the range Hilbert space, the other Hilbert space. Y need not be in the range of t or something. It is just some y. See, that's very important. Y need not be in the range of t or something. So that is why the reference to k, h are important here. Y is just in k. You have defined operator t from d of t, which is contained in h. So t may not be defined on whole of h, and it's landing up in k. Okay, and the range of t is something, some subspace. But this y may come from anywhere in k. Okay, so this reference to h and k, all these things are important here in when you define unbounded operators. Okay, so now the definition. Take d star, or which is equal to d of t star, whatever. I'm going to define t star, okay, which is also equal to d star, equal to all those y in k satisfying y satisfies the above condition, 1 or 2. I mean, of course, they are both equivalent condition, 1 or 2. Okay. First notice. If you have tx y equal to xz for all x in d of t, okay, equal to xz1 equal to xz2, then z1 equal to z2. So this z is uniquely determined. There exists the z is the second condition. No, there exists the z such that this happens. Okay, this z is uniquely determined. That is the z is uniquely determined. So z is in h. Sorry. Uniquely determined. Okay. Maybe I will write it small. Not. So the z is uniquely determined. So this map ty, so define t star of y. I mean, this all are, you are fixing a y, and for that all these conditions are there. So t star y equal to z. You can define. This is well defined. Right? The z is uniquely determined. So t star y equal to z is well defined. So you have a So Y is all such collection. So we have an unbounded operator, T star from D star, which you call it as D of T star, okay, to H is adjoint, which is a well-defined operator. It's called the adjoint of T. Shall we go through the definition again? You are given a T. So it's important that T is densely defined. Otherwise, you can't do that. Because you are extending to H and you are doing that. So you need T to be densely defined. T star may not be densely defined. Okay, this is for the existence of T star. Okay, T is densely defined, then we can, by this prescription, we can define T star. So T star is all those Y which satisfies this condition. Okay, all those Y which satisfies that condition, which give rise to a bounded operator. X going to Txy is a bounded operator. Okay, that is what is all those Y's. You take the collection of all those Y's. Okay, that is D star. So for that, there will exist a Z like this. So you define T star of Y equal to Z. Okay, that is the definition of T star. T star is defined on some D star, which is contained in K. So given a T from H to K, there exists a T star from K to H, which satisfies this. That is okay. So I mean, let me maybe repeat it. T is from D to K. This is dense. D contained in, sorry, it's the other way. Contained in H is dense. Then there exists a T. There exists a T star from D star to H such that Txy equal to, that is how it is defined, T star. This is the Z here. So T star of Y. Okay. The same condition which you have seen in the bounded case. Okay. This is, so if it is densely defined, then there exists an adjoint operator. Okay. Then we want to see conditions when it is the T star is also densely defined. We want to see the conditions later. So that is the point of the rest of the class. Okay. Okay. So now T star is also unique because when it satisfies this condition, so suppose there cannot exist two operators like that, because this I mean, see, first of all, if there exist two operators, let me not write all that, but it will be clear. See, suppose there exist two operators. First of all, they have to have the domain. Okay, and the domain will be same because all those I mean, this is true for all. This is true for all X in D and Y in D star. Okay. So we have fixed the Y star without the, I mean, the D star is fixed without any reference to, I mean, star or something. Okay, D star is something all those Y satisfying that. Okay, and from D star there, so the domain is fixed. So from D star there will exist only one operator which satisfies this condition. When it satisfies this condition, because the dt is dense, you cannot have two. I mean, this T star Y is uniquely defined. Okay. And another thing is this T star is also linear. You have to prove it's linear. That is linear because, I mean, by this prescription, the element of T star Y, I mean, this prescription, whatever this is equal to some Z here. There will exist a unique Z. There cannot exist two Z1 and Z2 here that we have seen. Okay. So if T star of alpha Z, alpha Y equal to alpha times T star Y, because alpha times T star Y will satisfy this equation with alpha here. We have an alpha here. Okay. If we have if you have an alpha here, you will get an, then you can take the alpha out, you can write the whole thing and you will get the alpha here. Okay. By the uniqueness of the Z, okay, this T star is a linear operator. Are you convinced? Just think about it. T star is linear. T star is linear means what? T star, we want T star of alpha y1 plus y2 should be equal to alpha of T star y1 plus T star of y2, right? Okay. Now the point is, if you use this equation, if you have alpha y1 plus alpha y2 in the place of y, then you write this alpha of T star y1 T star in here. This equation will be satisfied. So that will imply T star of alpha y1 plus y2, alpha y1 plus y2 should be equal to this. Okay. So this implies linear. So linearity of T star follows from uniqueness of Z. Z in the lemma, in the proposition. Okay. The proposition we have a Z. Okay. It is the uniqueness of the Z says that this is linear. Okay. And T star is also linear. You can just check. Okay. Sorry, T star is also unique. T star is linear, this was. Okay. So the definition is clear. T star is clear, no? We'll go to the. Also, I forgot to bring the paper. Let's keep it. I can't find. So there is. So notice this is a note. Note the following: if S is some operator, okay, S is some operator from some D of S to K, okay, and T is another operator from D of T. Sorry, D of is the other way. I want to write the S is some operator from D of S, which is contained in K to H. Okay. And T is an operator from D of T to K. This is contained in H. Then, if and further, and if it satisfies this condition, T of xy equal to x sy for all x in D of T, y in D of S. Okay. Then I didn't say what. I have to make a definition. Sorry. Then let me make a definition and come back here. Okay. So this is another definition. So if we have a T, which is defined from, unfortunately, this unbounded operator thing is maybe a bit messy because always we have to refer to the domain and all that. Okay. D of T to K. Okay. Then the graph of T I have already written. What is graph of T? Graph of T is equal to all those x, tx, okay, x in domain of T, instead of the domain of T, which is contained in H direction K. Okay. So the point is, if you know the graph of T, then you know the operator. Graph of T is a subspace of H direction K. Okay. If you know that subspace, you know T, right? You know all the elements X in Tx. You have all. So you know what is the domain. You just project it onto the first two coordinate. That is the domain. You know the domain. To know an unbounded operator, you have to know the domain and how does it act on the domain. That's all you have to know. So once you know the graph, I mean, once you know the operator, you know the graph by this. Once you know the graph, you project it onto the first two coordinate, you get the domain, and then the second coordinate will tell you what is the action. Okay, so you know, so instead of working on unbounded operator, you can work with graphs. If you tell someone the graph, this is the graph, then you know the unbounded operator. Okay, so that we say T is contained in S. Okay, if graph of T is contained in graph of S, a subspace. They are subspaces, no? If graph of T is contained in graph of S, we say T is contained in S. Okay. So this is the definition. And another definition is T is said to be closed. I mean, the operator is said to be closed if graph of T is closed. Okay. So we talk about operator containing in another. So what does containment means? Okay, what does this mean? T is contained in S means
The restriction.
domain of T is contained in domain of S, number one. I mean, D of T is contained in D of S. Okay. D of S. And S restricted to domain of T equal to T. That's all. S of X equal to T of X on the domain of T. Okay, that's all. So this is what the containment. Okay. And graph T being closed, I said already, I have said. Xn converges to X, Txn converges to Y. Okay, I will also say what it means. That is, G of T is closed is equivalent to saying Xn containing in domain of T. Okay. And Yn. No, that's not. Xn is enough. Sorry. Okay. Such that Xn converges to X and Txn converges to Y. Then X is in domain of T and Tx equal to Y. That is what it means by graph T is closed. So this is the definition. I mean, for bounded operator, you don't need, it will be defined already. But here you have to say that X is in the domain of T. That's all. That's one more condition. And Tx should be equal to Y. Okay. Okay. So with this, I want to say the following. If you have an operator S from K contain, not K, from the domain of S containing in K to H, which sat and T is an operator, something like that, then Txy equal to Sxy. I mean, it satisfies that condition. Can you say what is the relation between S and T? Then S is contained in T star. I mean, this says that the Y is in the domain of ds. Okay. But that condition will say Y is in the domain of T star also. Okay. So domain of S is contained in domain of T star. And there they coincide. S coincide with T star because of this condition. So S is contained in T star. Okay. So if this condition is satisfied, that doesn't mean S is equal to T star. See, this is the difference between bounded operator and unbounded operator. If something satisfies that inner product condition for all X and something, in bounded operator, that will mean S equal to T star. Okay. Here it's not like that. It means S is contained in T star. T star may have a bigger domain. Okay. Okay. So that's what I want to say. So we have defined containment. We have defined all that. Okay. Closed operator. We have defined examples. Examples we have already seen differential operator. So we can have another example. Which is the example we will be interested in when we do spectral theorem.
Here do we mean that S and T both are densely defined?
No need. I mean, if T is densely defined, then only you can have that joint. So S will automatically be densely defined. S is T has to be densely defined. It is important that T is densely defined. You are right. Here, right? If S is densely defined, then T is densely defined. Where am I saying? If S is not densely defined, S is just an operator. T is densely defined. Okay. T is dense. T is densely defined. So T star exists. Okay. S is some operator which satisfies this condition. Then S is contained in T star. Okay. T is densely defined. Okay. So what is next? So let us do some remark or something. No, let us determine what is the T star. What is T star given a T? Proposition. It's not right. loosened. That's right. Okay. Now T from domain of T is densely defined. Then you have a T star. Then the graph of T star is nothing but you take the subspace Tx minus x. X is in H. Okay. Then you take the perp, orthogonal complement of this. That is the graph of T star. The statement is clear. You take all x in H and you define this subspace. That may not be a closed subspace, but you take the orthogonal complement. That is graph of T star. So in particular, graph of T star is closed. It's a closed subspace. Okay, so T star is closed operator. Okay. So T is densely defined. So we have a T star. Now you want to put this graph, the graph is determined. So you know what is T star precisely. Not precisely. Fine. This only gives a criterion. You should know all those x to do this, but you can to prove theorem, you can work with that. Okay. This says that this proves that T star is closed also. So it's very nice. Okay. Okay. First, we want to prove this. So two things we want to prove. We want to prove that graph of T star is contained in this, and this is contained in graph of T star. That's what you have to prove. Two subspaces are equal. This is the usual way of proving anything. So suppose xy is orthogonal to, it's orthogonal to the whole of thing. It's orthogonal to this subspace Tx minus x, x in H. Is orthogonal to this, all of that. That is I'm sorry. So we have we need to have something else. So this x is different. This is true for all x. Okay, so here I shouldn't use x here. Y is it or something. Okay, let's just write y is it. It's okay. This just means this inner product y is it. Inner product is Tx minus x equal to 0. That's what it means, right? So that is y Tx minus zx equals 0, or this is equal to this. Okay. This implies T star y equal to z. This implies, T star y equal to z. This implies y is in the, I just mean this. This implies y is in the domain of T star. By definition, this is how T star is defined. And T star y equal to z. Correct? You take the course, the conjugate here. So this is how it's done. So this implies one way. This implies. So this implies that whatever you call this as some, you used K, H, K, G or something. Okay. G perp is contained in graph of T star. Okay. This is what you have proved. You have taken an element in G perp, an element orthogonal to G. Then we said that it is in the graph of T star. It looks like this. I have taken an element Y is Z. I just wrote the definition. That means Y is in the domain of T, and then T star Y is exactly equal to Z. That's what I proved by the definition, very definition of adjoint and other thing, right? So this implies G perp is contained in G of T star. The other way is much simpler. So suppose to prove the other way, this way, this is this way, proving this is this way. Suppose something. So we have to prove something in this T star. So suppose Y, T star Y is in G of T star. Okay, that is how anything in T star will look like. Then Y, T star Y, you have to take the inner product with Tx and minus X. Yeah, with Tx and minus X for any X. Okay, I have taken an X in domain of T, and I have taken Y, T star Y in graph of T star. Then I am taking this inner product. This inner product is happening X direction K. That is why I have written a tuple, X direction K. This is equal to inner product of Y, Tx minus T star Y, X. But these two are equal by the definition of T star, right? This is equal to 0. Okay. So this implies G of T star is contained in the G perp. G is all those elements, Tx minus X. Okay. This is orthogonal. So let us look at the statement. The statement is G of T star. So I am defining the space capital G, which is all those Tx minus X, where X coming from H. Okay. I am saying G of T star is a perp of that. So first I took an element in the perp. So that means it satisfies the orthogonality condition. Then I proved that Y is in the domain of T star and Z is precisely T star Y. Then I proved something in the G graph of T star that is orthogonal to G. That's all. So these two are equal. Okay, no? It's okay. Any problem? It just follows directly from definition. Okay. And it's important you should remember this. Graph of T star is Tx minus X perp. Okay. Shall we go to the next statement? Shall I write it? I'm trying, but I somehow write it in big letters. Let me try to write small letters. Okay. So these are all another remark. Okay. So what is the remark? You have some subset S is contained in H direct sum K. Okay. Anyway, these things are in Sundar's book and following from that. Okay. I mean, any unbounded operator book on unbounded operator will deal with these things. These theorems will be there. Okay. S is contained in S direct sum K. And then S is equal to graph of T for some T. For some T from D contained in H to K. Okay. Is equivalent to saying 0y is in S implies y equals 0. This condition. I write it as a proposition by remark. I mean, it's actually direct, but let us prove it. So suppose, so you have some arbitrary subspace. You have some arbitrary subspace containing H direct sum K. And you want to say that that is graph of some operator T, if and only if it satisfies this condition. So suppose it is graph of some operator T, okay, and 0 y is in S, that means 0 is in the domain of something. I mean, you assume that it's a graph of something. Okay, 0 y is in S means 0 is in the domain of course, 0 is always in the domain of T. T of 0 has to be 0. So that is clear. So 0 y is in S means y has to be 0. That is clear. Only so this way is clear. And this way, suppose if it satisfies this condition, then take domain of T to be equal to projection on the first coordinate. Okay, projection P1 of S, first coordinate. Okay, first coordinate. And define projection onto the first coordinate. Now, if xy1 equal to xy2, that means xy1 equal to xy2. This implies 0 y1 minus y2 equals 0 0, right? Equal to xy1 equal to xy1 by 2. Then that means 0 y1 minus y2 is in S. This means y1 equal to y2. So there exists a y1, y2. So define T of x equal to y1, which is well defined. That's what the above verification shows. Okay. I mean, you want to project it onto the first coordinate, then whatever that second coordinate, whatever the element you get, you want to define. But there is only unique element there because of that condition. Okay. That is clear because so that is why we verified that. Because 0 has a unique connecting coordinate there. So similarly, that will happen for everything because it's a subspace. Okay. Sure. Which is well defined. So this is clear. So this is how you see whether something is a graph of T or not. Okay. Okay. So next definition. T. I don't T of T is said to be closable if there exists a T closure containing T. There exists a closed operator T. T is contained in some closed operator. That's what we know. What does mean by an operator contained in another operator? If the graph is contained, then we say that operator is contained in another operator. Okay. If T is contained in S for some closed F, closed operator, yes, it is contained in some closed operator. Okay. The smallest closed operator is what is called closure of this. Smallest means, what is smallest? You take the intersection of all the graphs. Okay. I mean, you take the intersection of all the closed graph containing the graph of this. There exists one is the statement. If it is a closable operator, then there exists one. You take the intersection of all, if there is nothing, that is the one. Okay. Take all the intersection of all of that. So the smallest closed operator such that T contained in closed operator, T contained in T closure is the closure of that. Okay. Closure of T. So an operator can be closed. It is just the see, the idea is you take the graph. Okay. Graph has a closure. Take the closure, but that should be determined by an operator. So that you can check by the previous condition. Okay, the previous condition we have. This condition. This says that when some subspace is a graph, use this condition to check whether that subspace is a graph. If the closure is a graph, then it gives an operator. Okay, that operator is a closure. So you take you just take the closure of the graph. If you have a T, you take the graph of T and close it. If that is given by an operator, and that is the closure. Okay. So now maybe another proposition. This is also a remark only, the proposition. T is closable is equivalent to this condition. Xn contained in domain of T, DFT. Sometime I write domain of T, sometime I DFT, it's okay. Domain of T. Xn converges to 0. And T of Xn converges to Y. Then Y equal to 0. That's all. That's a simple condition. Okay. Of course, if it is closable, this is clear. Closable means what? Its closure is, its closure is given by an operator. Okay. That means Xn converges to 0, Txn converges to Y means 0, Y is in the closure. 0, Y is in the closure, which is given by an operator. By the previous statement, Y has to be 0. I just worriedly say the thing and you get convinced. This is an exercise. Okay.
Can we think of it some way that T restricted to the domain is a bounded operator?
No, T restricted to which T?
The T, which is a closable operator. So
T is a closable operator.
So it is when restricted to the domain, it is
domain of what?
Domain of T.
It is defined only there. What is that?
On the domain, as a substance of it is bounded because it continues at 0.
It is not continuous at 0. It is not continuous at 0. Continuous at 0 means Xn goes to 0, T of Xn should go to 0. It doesn't say that. See, look at that. It doesn't say that. See, we should be very careful with them. It is unbounded. That is what we are dealing with, unbounded operators. T is defined on domain of T. And how do you say it is restricted to domain of T is bounded? It is unbounded by definition. So there is nothing like that. It will not work like that. Closed operator T is closed graph theorem says that if it satisfies this condition, then it is bounded, which does not hold when D of T is not closed. D of T itself is not a Hilbert space or Banach space. It will not work. That is the idea. Here it says Xn has to, it is a condition, much stronger condition. Xn has to go to 0. Txn is going to some Y. It has to converge. Xn may go to 0, Txn may not converge. It may blow up. See, that is the property of unbounded operator. Okay. Xn will go to 0, differential operator. You can find something, Xn will go to 0, Txn will go somewhere. It will not go to 0. Okay. If it goes to 0, that is continuity, of course. Okay. That continuity will not happen here. It is not continuity. This says only graph is closed. This is different. Okay. So say Xn going, so this is good that you asked. It's very, very important to clarify this. Okay. Some closed, that is what I gave the example of a differential operator. Differential operator has closed graph. F1 converges to F. F1 prime converges to G uniformly, everything uniformly. F1 converges to F, F1 prime will not converge to F prime in derivative. Okay. But if F1 converges to F and F1 prime converges to some G, then F prime should be equal to G. This is a completely different statement. Okay. The graph is closed. That will happen. The graph is closed. But the operator is not continuous. Okay. So good that we get clarified about this. Okay. It's good you should ask such questions, even if you think it's absurd, don't worry about it, you should ask. Okay. So this is something different. So what is so let us look at the proof again. T is closable. That means the graph of T closure is given by an operator. Okay. Now, if Xn converges to 0, T of Xn converges to Y, that means 0, Y is in the closure of graph of T. Right? See this way. 0, Y, whatever that condition is in I am not writing the condition, okay, is in the graph of T closure. But you are saying that it is closable. Closable means this is equal to G of some T closure for some operator. So this implies Y equal to 0 by the condition we have just written. If something is a graph of something, then 0, Y is in that set, then it is like this. Okay. Conversely, if Conversely, where is it? The proposition is here. Conversely, if it satisfies this condition, okay, if something 0y is in the closure, then it is precisely equal to that. From the earlier condition, it follows. I mean, conversely, if this condition is satisfied, so suppose 0y is in the graph of t closure, then it says y is equal to 0. So t is closable, right? So it's both the things are clear, right? Okay. Maybe I give an assignment. So which is, you can write these things. T is densely defined. Then, and S, T, S both are densely defined. Okay. Let's say S is contained in T and S is densely defined. Okay. Then T is also densely defined. T is a bigger operator. Okay. S is densely defined. Then what do you expect? T star is contained in S star. So T is contained in S, T star will contain in S star. Okay. You have to verify that domain of T star is contained in domain of S star. And when you restrict, you have to appeal to the earlier thing. Okay. Very easy. Just you have to understand the domain and all that. Okay, that's all. Okay. So I will take some, since we started around 20, it has only 1 hour has passed. So I will take some more time. You're tired or something? Someone want to have a smoke or something? Here things are changed. When we were at ISI, I mean, we used to smoke in the class long back. But things have changed after, I mean, Anbumani Ramadas was a minister. At some point, he banned everywhere smoking, and things have changed. Anyway, you can't smoke here. This is AC room. So, we will continue. Okay, proposition. I was a smoker. I stopped smoking. I don't encourage smoking. I stopped long back. It was a very, I used to smoke 2 packets a day, but I stopped. Not a good thing. Okay. So what is the proposition? The proposition is T is T, of course, T is defined from domain of T. I write all the time. If I don't write, please take it like that. Okay. Is densely defined. Okay. T is closable. Okay. Is equivalent to saying T star is densely defined. Okay. So let's prove this. T is closable. T is densely defined. So we already have T star. Okay. So already you have a T star. Now we want to show that T star is densely defined. T is closable. We want to show T star is densely defined. T star is densely defined means what? Let Y is orthogonal to domain of T star. Okay. Then we want to prove that Y is 0. That's what we want to prove. Okay. So, I mean, the statement of the proposition is T is closable is equal to T star is densely defined. Okay. So suppose T is closable, that is there exists a closed operator. Okay. Such that T, I mean, containing T. So suppose Y is domain of T star. Okay. So Y is in domain of T star. Y is orthogonal to T star. To consider this Y0. This is certainly orthogonal to graph of T star. Right? Graph of T star will contain T star Y, T star Y. Okay. So graph of T star will contain something, some Y, T star Y. I mean, Z, T star Z. Okay. And Y is orthogonal to Z. 0 is orthogonal to everything. Okay. So this is orthogonal to graph of T star. Okay. But then we know that this is equal to, this implies Y0 is in the closure of this Tx minus X. X is in domain of T. Closure. I mean, G of T star is perp of this. Okay. I mean, G of T perp is equal to this. This, I mean, G of T star is the perp of this. That means this closure is equal to G of T star perp, right? G of T star is equal to perp of this. If M is orthogonal to some set S, M is, I mean, we have proved that S, the smallest closed subspace generated by S is S double perp. S perp perp. Okay. So the perp of this is that. Okay. So the perp of that is closure of this, right? Okay. That's what I'm saying.
Don't we need to take a span of this?
And this is subspace, no?
Or is it
Subspace. Okay. Okay. So this implies, but then we have assumed that T is closure. T is closed. Okay. Now this implies 0y is in the G of T closure, which is equal to G of T closure. By the earlier prescription, this implies, by earlier proposition, this implies Y is 0. That's what we want to prove. Y is orthogonal to D of T star. We want to prove Y is 0. Okay. This implies D of T star is densely defined. Dense means anything orthogonal to whole of that is 0. That's what dense means. Dense means this means, I mean, orthogonal complement is 0 means the closure of whatever we are considering is everything. So that means that should be dense. Okay. I mean, it's already a subspace. D of T star is subspace. Okay. So this thing D of T star is dense. Okay. So Y is orthogonal to this. I have used the earlier whatever we have proved, and from that we have got this. Okay. Conversely, what do you have to do? If it is densely, T star is densely defined, then T is closable. That's what we want to do. This is very easy. T star is densely defined. This implies T star exists. T star exists. Okay. And T star satisfies this condition, no? Y T star Y X T star Y is equal to T star X Y. This implies T is contained in T star, right? By the definition. We already noticed this, right? So, but T star, we have already proved that star of anything is closed. So this implies this is closed operator. So this implies T is closable. Okay. So T is closable is equivalent to saying T star is well densely defined. Remember that this closable, all those things has to do with graph. Domain of T is dense. That's not closed subspace. Okay. When we say something is closed, it has to do with the graph. Graph is closed. Okay. So let us just write the corollary and stop. Okay. If T is closed operator, I mean, in fact, this says that T star star is the smallest closed thing. Smallest closed. Then if T, no, I have to prove it. If T is closed, then T closure, then T equal to T double star. I mean, I want to prove that if T is closable, let's just do that. Sorry. Later, different thing. Corollary. T is closable. Of course, that means T star is densely defined. So T star star exists. Then T closure is equal to T star star. In particular, if T is closed operator, T is equal to T star star. Okay. So T is closable. So we know that T star star exists. I mean, T is closable. We have proved that T star is densely defined. That means T double star exists, which is star of T star. Okay. And that contains T closed. That contains T, and it's a closed operator containing T. So we only have to prove that T is double star actually coincide with T. I mean, graph of T double star is exactly closure of graph of T. That's what you have to prove. Okay. So let us define an operator. Define W from H direct sum K to K direct sum H, defined by X, Y going to Y minus X. I mean, remember that we have already, right? Okay, then W star, which is just the inverse of this unitary. W star is from, again, K direct sum H to H direct sum K, which is given by W star of YX is equal to minus XY, right? It's clear. These two are inverse of each other. Okay, if you just work it out, it's clear. So these are all unitaries. Okay, it just flips. So it will preserve the inner product, right? It just flips. It's the same thing. And then it changes to minus sign. Okay, one of them. So it's all unitary. Okay. So our earlier theorem says that graph of T double star equal to this W of. So this in particular says that, I mean, W is just some sort of minus of that, right? You flip the coordinate and takes the minus of that. Here you have the minus in the second coordinate, something like that. Okay, let me write it. So this is equal to, I mean, let me write it. Minus W star of graph of, see, W is from H direct sum K to K direct sum H. But T star star is, C star star is connected to T star through something. I mean, see, we have this theorem, no? The graph of T is equal to, we have, let me write it. Let me write it here and erase. Graph of T is equal to this Tx minus X perp of this, right? This is for T defined from H to K. If T star is defined from K to H, you have to reverse the role of K and H here. Okay? Reverse the role of K and H. Okay? And then you have to take. So what I'm saying is that W will be minus of W star. Okay, we have defined W from H direction K to here. So that direction is just the minus of D star, which is equal to this star, graph of T star per. Minus of W star, then per outside. See, you just verify that if you have a unitary defined from any two Hilbert space, H1 to H2, okay, then K is contained in some subspace, closed subspace, then U of K per is equal to U of K per. Unitary satisfies this condition because it preserves the inner product. You write down the definition of per unitary everything. Since it preserves the inner product, it will follow. Okay. So you can take the perp and all these things outside. I mean, this is not you acting on a subspace you are taking. So minus does not matter. I mean, since there is a subspace, minus subspace is same subspace itself. So minus does not matter. Since W star is unitary, all you get is W star of G of T star per itself. Okay. 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 Now now we have that, see, G of T is G of T star is equal to W of G of T per, right? G of T per. So W star will go away. All you get is G of T star is G of T star is W of G of, let me write it. Okay, why not one more step? W star of W of G of T whole perp, then I take the perp inside and perp outside. You can take the W everything out. W star W is 1. So this is just G of T double perp, which is equal to G of T closure, which is equal to G of T closure. That's all. So this implies T closure equal to T double star. In particular, if T is closed itself, T equal to T double star. So this adjoint is a very nice map if you have the collection of closed operators. You don't have to worry about containment and all that. If you have only closed operators, if you don't deal, you have a densely defined operator and the graph is closed, then it's called a closed operator. If you have a collection of closed operators, then you have then what is it? Then the star is adjoint is closed among this collection. The star operation is closed among this collection. That's what this is. So that's what we will deal with. Okay. What we will deal with self-adjoint operators, which are closed already. T star equal to T, that makes sense. So that's what we will do. Okay. So I stop here.